Oh, I've been muted. I apologize. I'm sorry. Thank you everyone for joining. This is a tidal disruption events and transients session 2. We had an earlier session this morning. Remember to use the Q&A feature down at the bottom to enter your questions. If you have any questions, the speakers will address those questions at the end of their talks. And we may have some time at the end for a group Q&A as well. Thank you. Without further ado, let's start with our first speaker, Enrico Ramirez-Ruiz.
Thank you, Rodolfo. Let me know if you can see my screen. Yeah, I'm good. Thank you. Thank you so much, everyone, for being here. Hope you and your loved ones are safe and healthy. Thank you for giving me the opportunity to speak to you virtually about this incredible topic. So I'll be touching on aspects of the tidal disruption of supermassive black holes, and I want to really focus, briefly about what we can learn and what we have learned, and sort of the challenges, but also the excitement behind the, the recent dramatic progress in the field. And I just want to highlight, the work here of the grad students, Brenna, Mockler, who you're going to have the opportunity to hear, and Jamie Law-Smith, which I will be presenting to here. So what can we learn in tidal disruption? So of course, we can unveil a lot of the quests and sources in the local universe. As you know, most of the galaxies in the contemporary universe are basically starved of fuel. And tidal disruption, allows the opportunity to really do black hole demographics and really understand the population of black holes in the nearby universe. Interestingly, we want to also characterize stellar nuclei, both the dynamics and the properties of these dense stellar systems. And ultimately, we want to understand, how accretion turns, ultimately into a transient feature. And it is important to highlight that, tidal disruption events change by orders of magnitude in luminosity in timescales of years. So, that allows to sort of investigate what I call black hole gastronomy, the accretion productions of jets, winds, and outflows. And we're going to hear a lot about that in the session today. So I'm going to focus on two aspects. I'm going to give you a little bit of an update of where we are in doing tidal disruption simulations and why I actually think they're incredibly valuable, because they will, they're incredibly powerful in order to constrain the properties of the host black hole. And Brenna in her talk is going to talk about that. And I'm going to also focus about, what can we learn about the object that is disrupted? And then I'll talk about some challenges and open questions and lessons that we have learned along the way. Oops. The movie. So as you know, the central supermassive black hole basically influenced the dynamics of stars within the sphere of influence. And these stars follow these really complicated orbital properties because they're influenced both by the central black hole, but also by all the other stars. And there is a non-negligible probability that one of those interactions will send the star into what we call a radial lost common orbit, and it will get incredibly close to a black hole. Close enough that it can no longer be treated as a point mass. So when that happens, this is usually when the star approaches what we call the tidal radius. And here I just give you a characteristic scale. This is, of course, where the black hole's tidal force is compared to the gravitational binding energy of the star. What happens? Well, as the star basically approaches, and here I'm going to denote two characteristic scales, which are incredibly important for what I'm going to describe. One is the pericenter distance, the minimum approach distance, and the other one is, of course, the tidal radius. And we usually use the penetration factor as a scale. So an encounter of beta of 1 basically means that the pericenter distance is the tidal radius, and anything with increasing beta becomes, a progressively more intense encounter because you're tracing deeper in the potential of the black hole. So as the star is falling in, it develops a quadrupole distortion whose amplitude reaches a order unity at the time of the tidal radius. And there's both, the drastic torque and the large surface velocities that actually combine to ultimately disrupt the star. So what it's incredibly important for what we're going to discuss is, of course, the tidal radius is an average property. Stars are centrally concentrated depending not only on their mass, but in their evolutionary age. And usually there's a surviving core that remains. Half of the material that is actually disrupted from the core, remains bound. Half of it, remains unbound. And then it becomes hydrodynamically a very interesting problem, because you have to resolve these three-body problem. You have to think about, how both the core and the black hole actually fight for, getting a hold of that mass. So I'm going to show you sort of some of the state-of-the-art simulations that we have been developed along with other groups. Now we are in a position in which we can actually take a star at any evolutionary age, any mass, and actually disrupt it hydrodynamically. So what you're seeing here, you're in the center of mass of the star. The black hole is coming in a parabolic orbit towards the star. As you can see, very, very strong quadrupole distortion, large surface velocities, significant fraction of the mass is actually ejected, and the core remains. And what is incredibly important for us is how does ultimately the bound material falls back to the black hole. And that's what we call the feeding rate. Now, something that it's incredibly important to highlight is, of course, stars based on their mass and their stellar age vary in concentration. So here what we use, which is actually incredibly telling of the stellar structure, is the central core density compared to the average density in the bottom panel. And at the top panel, you actually see how both the central concentration of the star and its structure changes as a function of mass and age. And we actually are hoping that ultimately some of these features are ultimately reflected in the Lie curve, and whether there or not there's information that can tell us something about the type of star that got disrupted. And of course, as you know, low mass stars would not evolve very much, so they basically persist in a stellar structure. But stars very close, or above the IMF peak have significant transformations. And the idea is whether or not we can actually even try to get insight into the evolutionary state of the star. And I'm going to tell you ultimately that we need both Lie curves and spectra to do this effectively. So these are sort of the type of simulations here. What is shown at the top is basically in the top row, what is changing is beta over beta critical. Beta critical, of course, changes. This is when the star gets disrupted. And you can see, you can think of it as a beta in this direction, which is the depth and strength of the encounter. And then on the y-axis is kind of the stellar structure, which is here characterized as the ratio between the central density and the average density. And of course, things that are significantly more evolved have cores that are much denser, and therefore the cores sort of resist the disruption. So this is interesting because we're now in this parameter space where there's actually significant amount of degeneracy between, can I tell apart the intensity of that encounter and also the evolutionary state and mass of the star. And ultimately, this is imprinted in the Lie curve. And what we can actually calculate incredibly accurate is how does the bound material ultimately returns to the black hole. So this is sort of at the end state of a fully disrupted simulation. You see there for reference what was the initial size of the star. So we have to basically run the simulations for hundreds of thousands of dynamical timescales. The material that is closest to the black hole is the material that is actually going to return the fastest. And ultimately, what you do, to calculate the return of material to pericenter is basically you really need to understand these first term that we have here. That term is basically given by the hydrodynamical simulations, which is really the energy per unit mass that was injected. While the second term, it's really from Kepler's law, and it tells you basically, depending on the position of that fluid element, what is its orbital time scale to fall back. In a classical paper, Martin Rees said, well, if the MDE is actually flat, I go down to the classical t to the minus 5/3 law. And that was what was characteristic of what we thought indicative of the presence of a tidal disruption. So as you can see now, we're able to calculate the return of mass to pericenter, which here is as a function of basically how centrally concentrated the star. And I'm just showing here for full disruptions. This is the new calculations by Jamie. And as you can see, there are imprints of the stellar structure, both in the rise and in the decay phase. So this, of course, is incredibly interesting, whether or not ultimately, and I think as Brenna will rightly convince you that the luminosity actually of the transient follows very closely the fallback curves. However, things become a little bit more complicated once you add the strength of the encounter. Of course, in this particular case at low beta, you're taking a smaller amount of mass, and as you go further and further, you get to fully disrupted. And here I show two solar mass objects at different evolutionary stages. And there's some imprint in the light curve, but there's certainly a degeneracy between the type of star that got disrupted, the size and quality of the interaction, as well as the strength. So we actually think that in order to break some of these degeneracies, thinking about composition is essential. In particular, because when you think about the mass that returns back to the black hole, sort of reflects the interior composition of the star. And if you have an evolved star that, say, for example, undergoing the CNO cycle, you're going to see drastic changes in the composition. What I show here is two stars, a 3 solar mass star and a 1 solar mass star. And for example, I want you to focus on the nitrogen composition, which is the green one, as a function of how supersolar the nitrogen is as a function of time scale for the return of the material. And as you can see, if you compare a 3 solar mass, you get significant amount of nitrogen when compared to a 1 solar mass star. But even in a 1 solar mass star, which had had enough time to evolve, you see supersolar nitrogen abundances. And the question is, can that be reflected in actually seeing a nitrogen-rich tidal disruption event? So not only the strength, but where in time these abundance anomaly appear is incredibly telling about what type of star you actually disrupted. So if you can combine both the spectral information and the light curve, actually you can learn about the type of star, which we are incredibly excited. So of course, this field has been revolutionized. So that this was at the end, at the end before really synoptic surveys took place. And a lot of the characterization of these flares depend on whether or not the decay followed these t to the -5/3. Things have dramatically changed. This is probably one of the most beautiful events. And what you can actually see there is that the hydrodynamical simulations, which are plotted there, do an incredibly effective job at describing the evolution of the flare, particularly the arise and the decay. So, and as Brenna will advocate, it seems that the total bolometric luminosity actually follows the fallback rate to pericenter incredibly accurate. And then we're going to talk a little bit about what other things we need in addition, such that the black hole accretion rate actually follows the fallback rate. What it's interesting, this is an example in which we have used more simplified models that do not have age as a variable. But this is the sort of information that you can extract when you actually fit the light curve based on the hydrodynamical models. As you can see there, you can actually determine, relatively accurate the black hole mass, because the time of peak depends sensitively on the black hole mass, and Brenna is going to expand on that. I think that characteristic is going to make the light curves incredibly useful to actually learn about demographics. But you start having a much harder time actually discerning the mass of the object that got disrupted. In this particular case, we can infer when the tidal disruption took place, more or less. We know that the black hole mass that we infer is comparable to that derived by the M sigma relation, which is plotted there in different blue shaded. And ultimately, the inference is that these objects are disrupting stars very close to the peak of the IMF, at least in this particular case. But without spectra, it's incredibly difficult to say anything more about the star. And that's something that we've been trying to pursue in significantly more detail. So this is the sort of seminal work that Brenna has taken place by utilizing this idea that the total bolometric luminosity follows the fallback rate. And sort of the overall lessons that we have learned in the field is that the systems peaks on timescales of weeks to a couple of months. That peak timescale is strongly correlates with black hole mass. The color is relatively constant, but not perfect. It's well fitted by sort of a black body at sort of 10 to the 4 Kelvin. The majority of the light seem to be emitted, particularly in those ones that are selected in the optical UV. The peak luminosities are comparable to the Eddington limit, or close to the Eddington limit of the black hole. And what we see, and of course this is a Chandra conference, is that we see usually much less activity in the X-rays that's suggested by the optical luminosity. And some of the argument I think that is being put forward, that significant amount of obscuration is actually reprocessing the light from the black hole into the optical UV. So I'm going to briefly discuss some of the challenges and open questions. We used to think, that the black hole, as material falls in, the accretion disk gets assembled almost instantaneously. That's not entirely the case. So in order for the light curve to follow the fallback rate, what you need is basically the black hole assembly to be, relatively promptly, and then the viscous time scale to be short compared to the infalling time scale. And a significant amount of work has been done in trying to really understand how you ultimately go from these highly eccentric orbits to a circular, accretion disk. So in order to do that, I'm going to show you a movie, recently run movie. You'll be the first ones to see. This is a star that is basically getting disrupted, and here the majority of the circularization is actually driven by hydrodynamical interactions. There's also incredibly important for black holes that are more massive that I want to show you here, GR effects. But as you can see, significant amount of energy dissipation ultimately leads to effective circularization. And I think there's significant amount of debate in the field as to whether or not that can be achieved, say, for example, without GR. And how does this depend with black hole mass, and whether or not that, there will be a significant fraction currently of TDEs that we're missing just because the circularization is taking too long. Alternatively, as Brenna will talk about, there's also alternative theories in which actually the vast majority of the luminosity is given by the interactions of these streams. And those follow very, very closely the fallback rate. I think to my, to my own belief, I think this result by Tiara Hong is probably one of the most exciting current results in the field, in which we actually think that we have actually seen, very, very early on, the formation of an accretion disk. Tiara clearly see here the blue and the red wing of the line component, and in principle was even able to get some estimate of the eccentricity of the disk, which is actually in close agreement with general relativistic simulation. So we are seeing that, deep inside, an accretion disk is formed, and there's of course significant amount of interest as to how you ultimately take the radiation, close to the last stable orbit of the black hole, with the vast majority of the luminosity gets produced, and then reprocess it in the optical. So sort of the cartoon that I'm showing you there on the right-hand side is sort of what I wanted to have in mind, that you have this kind of eccentric elliptical disk, and then some amount of material that is actually reprocessing the central source, either that a wind or sort of a quasi-hydrostatic structure there, that it's basically taking the high energy radiation and reprocessing it to the UV. So this has been incredibly exciting development about really for the first time having the opportunity to actually peek into the three-dimensional structure. I won't have time to talk about this, but we also and I think as Brad talked about, and they're pioneering the understanding of kind of the broad line region structures of this system. So what it's incredibly interesting is that we're seeing broad line region, being actually formed in real time. And then questions are, how closely they resemble to those in AGN, especially because both the mass accretion rate and the luminosity are changing vastly during that period of time. So there's a significant amount of work that needs to be done, even empirically at this stage, to really try to unify the broad line features that we're seeing emanating from the systems. So this is an incredibly exciting time. It really highlights the point that I wanted to make about the importance of spectra. So something that we've been really working hard in trying to get a clue is, can we actually get the spectrum of stars that got disrupted by the black hole? Can we say anything about their mass? Can we say anything about their evolutionary state? And again, highlighting some of the point that we made before is, these, the fact that the spectrum of these systems actually show fairly strong nitrogen rich lines, which are basically highlighted there. And in this beautiful paper, there's basically nice comparison. For example, if you take SDSS composite spectrum, you really don't see the nitrogen line. But if you compare in some of these nitrogen-rich quasars, they have spectrum particularly that are relatively similar. And you can clearly see for assassin 14 Li, the clear nitrogen feature there. Now, those features require super solar abundance, and then just simply the presence of this line tells you something about the evolutionary state of the star, particularly if the remainings of that star, which basically were primarily scattering in the surrounding wind, ultimately the black hole illuminates that region, and that's where you see the nitrogen line features being produced. So you can play, for example, this exercise. This shows, again, mass of the star that got disrupted, evolutionary state of the star as a function of time. So you can think of it as things that are very close to the main sequence and are low mass will not have nitrogen enhancements because they haven't really undertaken significant amount of CNO burning. But if you go to higher mass and of course longer evolved systems, particularly at low mass, you can actually put constraints about the type of star that got disrupted. So in this particular case, you will say, well, this star certainly had to be higher than about 1.5 solar masses in order to have super solar abundances that are consistent with the strength of the nitrogen line that we see. So it is incredibly interesting now that we may be able to really combine the light curve with spectra to actually get into the properties of both the black hole and also the star. And there's a significant amount of work that needs to be done in the radiation transport in order to really understand how these lines are produced, their relative strengths, and so forth. Something interesting, for example, is of course, while you expect enhancements of nitrogen, you also expect a depletion of carbon. So looking at lines with similar ionization potentials of carbon and nitrogen has been a way that people have gone after nitrogen-rich quasars, for example. So something like that would be incredibly important in this particular case, where you have basically two lines with the same ionization potential, and the relative intensities tells you something directly about the abundances. And of course, in addition here, what I haven't sort of highlighted is that when the nitrogen appears in the light curve is very important. If you have a star that is not as evolved, that burning process, which is deep into the star, it's farther away from the black hole and it takes longer to fall back. So not only the intensity of the line, but where in the light curve it appears gives you some incredibly important clues. And this is work that Monica Gallegos Garcia did as an undergrad, and she's now a grad student at Northwestern. Okay, so if you want to, we talked a little bit about, the light curve, we talked about the spectrum, and what about the stellar populations that we're seeing? So something that it's been actually incredibly interesting, and it's sort of been difficult to explain, is that many of these tidal disruption candidates have been discovering these galaxies that have, incredibly strong Balmer line absorption, but they have weak emission lines. So they're basically, and I'll show it you in a second, but they're basically in the transition from turning off, and their starburst has an age that is sort of hundreds of mega years. And then the question is, how often this happens in these galaxies and how common these galaxies are. This was sort of revolutionized by Decker French, and you can see here, particularly if you look at, say, the delta feature there in some of the events, it's incredibly deep. These are sort of usually characterized as E+A galaxies, E as ellipticals, and A. These are the A features that arise, post starburst between hundreds of millions of years to a giga-year or so.
3 minutes.
So this is incredibly interesting because what I show here on the left plot is basically where SDSS galaxies lie. And those boxes that you see with very deep absorption features are where the TDEs happen. And as you can see, there's less than 1% of galaxies in the SDSS footprint that have, that can be considered as E+A, yet half of the tidal disruption events happen in these galaxies. So there's an overabundance by a factor of 50 of tidal disruption events in this system. So that means that the rate has to be drastically enhanced in the system. So these systems are basically in the process of quenching. They are in what it's called the green valley, as you can see that in the right-hand side. So it is incredibly interesting to try to tie this into rates. When you actually looked at the host galaxies, this is a beautiful comparison by Jamie Law Smith, in which he basically matched every single property that he can on the galaxies in terms of black hole mass, star formation, and then compare those that have, compared to those of TDEs. And as you can see, the matches have much less centrally concentrated cores, which in this particular case are characterized by the Sursec index. And you can see that these systems have high concentrations of stars in their centers. Of course, here we're far away from the sphere of influence based on the resolution, but it clearly hints at this idea that there is large densities of stars in the systems, and something is drastically helping enhancing the rate, either just because there's a significant fraction of stars, or maybe because there has been a merger, another black hole. So there's lots of debate as to why that's the case, which has been incredibly interesting. Okay, so just to finalize my talk, I hope I gave you, a very brief introduction of why we think these systems are incredibly interesting and how we have moved from, simple characterization of knowing that this is a tidal disruption event to actually try to infer some of the salient properties of both the black hole and the star that got disrupted. Brenna is going to talk in significant more detail about really getting at the black hole demographics and how you can utilize just even Likers alone to actually learn about the black hole. And I hope I convince you that there's some hope in really characterizing, the stellar mass distribution of objects that got disrupted by the black hole. But the sort of takeaway message is that we really need to combine both Likers and spectra, and of course improve our theoretical models so that we can actually go from the understanding of the fallback, which we really understand very well, to the much more complex circularization processes that ultimately form the accretion disk, how the mass is redistributed in that region, how the broadline region comes to play, how the accretion disk comes to play, and ultimately how the spectrum is formed. And another incredible thing about a tidal disruption event, and I think we're going to hear a lot about this, is that their accretion state changes very dramatically within one object. So it gives you the opportunity to really try to understand how the disks are assembled, how the broadline emission is actually built in real time, what sort of winds that you have, and as we'll hear later, the type of jets and whether or not every single one of these tidal disruption events is able to actually create a relativistic jet or not. So I'll stop there, and I'll thank you for your time, and we can take questions. Thank you so much.
Thank you. We have a couple of questions. The first is from Franz Bauer. I'm not sure if you're going to touch on these issues. It includes how ISM circumstellar environment might affect the disruption in the electromagnetic signatures. This could vary. Sorry, go ahead.
No, go ahead.
It continues to go on. This could vary from fully formed high accretion rate AGN disk to more modest accretion scenarios.
Yeah, so it's interesting to, when we looked at these E+A galaxies, there's actually a non-negligible, the fraction is difficult to compute, but in the order of, a third or so of these events that actually show some sort of AGN activity before the tidal disruption event took place. So the question is, if you already have an accretion disk, would that aid circularization? Would that help in forming a jet? You need to have significant amount of mass there in the region where the accretion disk is built in some way, just to give you a feeling, it's sort of the photosphere is about AU and you're putting a fraction of a solar mass. So if the accretion rate, is sort of a fraction of Eddington, certainly having a disk is being shown to actually change the properties. We also see, very kind of narrow emission features that are thought to have been produced relatively far away from the black hole, where the tidal disruption event wouldn't have had time to actually place material there. So the idea that there was an AGN activity to begin with, and there was a narrow line region already in place by the time the tidal disruption took place is important. And ultimately, some of the work done in the radio following up these systems, looking at really the deceleration of the blast wave and the jet, tells you something about the external medium and whether or not you expect significant acceleration in the radio. So there's a significant amount of work trying to pin that down. But unfortunately, the number of tidal disruption events that we have found that have a relativistic jet are small and have not increased, which is interesting.
Great. And then we have a question from Mary Saad. So we've seen the possibility of TDEs produced by supermassive black holes and intermediate mass black holes mentioned. Is it possible, at least in principle, for a stellar mass black hole to tidally disrupt a star?
Yes, yes. So there's a significant amount of excitement recently. For example, if you take the LIGO black holes, if the LIGO black holes, as some theories seem to indicate, may have formed dynamically in, say, dense star clusters, there, for example, there's the possibility of the systems disrupt stars. Of course, the stellar densities are high, the probability of these black holes to disrupt stars, and those stars, can aid growing in mass. They can produce some transients. So there's some work being done in trying to characterize that. Something that is incredibly interesting and exciting is that as you go to, of course, lower and lower mass black holes, there's other objects that can get disrupted. For example, white dwarfs. So there's some excitement about disrupting white dwarfs, in particular because you can ignite them through the tidal interaction. So in principle, you can actually see a thermonuclear transient from the center of a galaxy where you both see the accretion component, but also the radioactive energy injection into the remnant because of the ignition. So once you go to lower mass black holes, which of course the demographics we don't understand as well, I think there's a lot of excitement. But right now, I think whether or not these LIGO black holes in dense systems are disrupting stars and what sort of signatures they give is something that people are thinking just based on the rates and sort of some of the evidence that is pointing that these dynamical assembly may be actually the main way in which these black holes are actually made in the universe.
Great. We have one more question from Dong Yu. Thank you for the nice talk. I think we can all thank you for the nice talk. Do you take the rotation of any of the star into consideration in the simulation, and will it cause any difference?
So there's some slight difference. We have now run simulations with some rotation. There's some really beautiful work by Nick Stone thinking about these issues also analytically. The way that you can think about this is as the star gets to the tidal radius, the resultant torques are incredibly high. So by the time the object is being disrupted, the surface velocities are very close to the breakup velocities. So in order to really affect some of the mass distribution, you really need the star by the time it's, before it's actually getting disrupted, to have a rotational velocity that it's comparable or a significant fraction of the breakup velocity, which seems unlikely for some of these stars. But yes, those simulations have included rotation too. And also we try to look at misalignment between the axis of rotation with the orbital plane. And what we're seeing is we're not seeing drastic changes. There may be some small features early on in the light curve that you may be able to see. But yeah, that's a great question. Another important thing is there's also simulations trying to take into account the internal magnetic fields and whether or not there's amplification of the systems. And finally, something that would be actually quite exciting will be to actually see within our own galactic center whether we actually see any of the remnants of partial tidal disruptions that are still going around, and whether or not they have different compositions, they have different rotational profiles, different magnetic field amplifications, and can we actually ultimately see the survivors in our own galactic center.
Great, exciting stuff. So we have one more question. With regard to black hole gastronomy, I know you meant gas astronomy, but is the pun with the culinary meaning gastronomy intentional?
Yeah, it's sort of thinking about the digestion of a star and the digestion of matter. I think some people sometimes refer to this process as spoon feeding the black hole, because ultimately you can take a significant fraction of mass that it's in high concentration and put it incredibly close to the black hole, spread it in a very small region, and feed the black hole at very, very high rates for a short period of time, which is incredibly difficult to do, say, with a cloud, because of course the average density is smaller. But yes, it was a play of words.
Great. Great, thank you very much. Can the next speaker please set up? I made a little bit of an error on the next speaker, and I did not communicate their amount of time, so they'll be giving a little bit longer talk in this presentation. In case you're wondering, they're not going over unintentionally.
But yeah, we'll see what we get to, but I think it'll be good. Thanks so much for having me here. Oh, I need to start the actual slideshow. I will be talking about how we can, so I'm Brenna Mockler, I'm a grad student at Santa Cruz, and I will be talking about how we can learn about the engines powering tidal disruptions, the black holes and the accretion disks, et cetera, by modeling their light curves. And so Enrico mentioned this a lot in his talk, and I think also Bradchenko did. It appears that for tidal disruption events, the flare actually follows the expected fallback rate. And so what this means is that as the material returns bound to the black hole, you have this accreting fallback rate. But when we actually look at the light curves, it seems like the bolometric luminosity we see follows that fallback rate, meaning that if we fit the light curves, then we can actually extract information about the fallback rates and about the system that disrupted the star. In particular, a little teaser is that we can learn a lot about the black hole mass because the fallback rate is very dependent on the mass of the disrupting black hole. So here are a few relations that just show how the black hole mass impacts both the magnitude of the mass fallback rate and the time scale of the mass fallback rate. Essentially, as you increase the black hole mass, you're stretching the mass fallback rate out, and so the magnitude is lower and the time scale is longer. And so we focus on the time scale just because there are less other parameters that affect the time scale, and so we're better able to constrain the black hole mass using it, although both are important. And just to kind of give you a visual idea of what that looks like for a fallback rate, this is the mass fallback rate from a simulation with the mass fallback rate on the y-axis and the time in days on the x-axis. And it's the disruption of a 1 solar mass star by a 10 to the 5 solar mass black hole. And as we increase the mass of the black hole to 10 to the 6, the peak time scale increases from here 8 days to 24 days. Again, if we increase it to 10 to 7 solar mass black hole, the peak time scale increases again. 10 to 8 solar mass black hole, you get the idea. So basically, if the bolometric luminosity is approximately following the fallback rate, and you are looking at the disruption of a 10 to the 6 versus 10 to the 7 solar mass, or the disruption by a 10 to the 6 versus a 10 to the 7 solar mass black hole, you can tell the difference simply by looking at the time scale of the light curve. And of course, we do something a little bit more complicated when we're modeling the events, but a lot of our discerning power for the black hole mass comes from this relationship. So if we, when I think about modeling TDEs, I like to kind of think about it in a few different parts. First, there is this mass fallback rate from simulations, from hydro simulations. And then once you have actually, so that's modeling the disruption and the mass that returns. Once you have this, you need a model to show actually how the mass circularizes. We're not going to, we might have time to get to this at the end, but for now I'm going to focus on the other two parts. And the final part is the reprocessing layer. And so this is just modeling how the source luminosity is reprocessed so that we can compare it with observed light curves. And we do that really simply right now, but we'd like to, for now. So yes, for now we're focusing on the mass fallback rate and the reprocessing. If we have time, we'll go back to circularization. So Enrico talked about fallback rates a lot in his last presentation, so I hopefully don't have to spend too much time on this. But basically, this provides the engine, the source of energy in the model. And to do this, I use a library of simulations right now from Ramirez-Ruiz 2013, the process of updating it, as there's been a lot of new simulations run the last year or so. And you can see that they've been run for a variety of different impact parameters. And again, as you increase the impact parameter, more mass is bound to the black hole. And so you can see as beta increases, the mass fallback rate is higher. For the model, we interpolate in the impact parameter and then scale with the mass of the black hole and the mass of the star. Of course, then we need to actually reprocess this. We need to actually convert this mass into luminosity. And so we expect there to be stream collisions between these debris streams that will circularize the debris and form an accretion disk. And while these processes, either one or both, are are actually powering the light curve, we don't see them directly. Brad Schenko talked about this earlier. What we're actually seeing is luminosity from an optically thick photosphere. It seems like it's about 10 to the 14, 10 to the 15 centimeters on average. But this is why we have so many optical and UV. These are the optical and UV TDEs that we're talking about. They're much lower temperatures than we would expect if we were directly observing the accretion disk. And actually, so we don't know exactly how this is formed. However, recent simulations, both of the stream collision process and of the formation of the accretion disk, and of just the accretion disk, have shown that they get a lot of mass outflows, a lot of mass ejected. And this actually, when they estimate what the optically thick photosphere would look like with their like tau equal 1 surfaces in these simulations, it does seem to be fairly comparable with what we're getting in observation. So maybe we're getting a little bit closer to understanding what's going on there. However, because we can just model the photosphere, this makes it a lot simpler. So we, instead of modeling the intricacies of the stream collisions, we can just model the evolving photosphere. And while we'd like to go into more detail with the reprocessing for now, this simple model allows us, I'm actually gonna skip over that for time, but allows us to input this model into the MOSFET transient fitting code and use an MC fitter to fit the light curve. And this would not be possible if we had a more complicated reprocessing model, simply because it would take way too long to run an MC on it. But I highly recommend using MOSFET for all of your transient fitting needs. There's a lot of different models, not just the TDE one, so a little plug for MOSFET. But once we do this, we're able to fit a bunch of TDE light curves. And here are some of the example fits. As you can see, it seems the MOSFET TDE model works quite well, particularly when you have good measurements around peak. So in the middle column, those events have better measurements around peak, and so the light curves are more constrained than, for example, in the left column where there aren't even upper limits, and so there's a lot more uncertainty. And this makes sense. If we can constrain the black hole mass better, and also just the time scale better, we're able to constrain the light curve better.
3 minutes.
Perhaps most exciting, what?
3 minutes left in the time.
Perhaps most exciting here is that we can estimate the black hole mass. And so Enrico also talked about this earlier. Here I'm comparing the black hole masses that we get with MOSFET with the M sigma relation. So the black hole masses for MOSFET are in like the wine red color, and the other ones are in black and gray. And the AGN measurements are from Zhao et al. 2011. Or the other measurements are from Zhao et al. 2011, and they happen to mostly be from AGN just because TDEs are occurring around these lower mass black holes. If their black hole is too large, the star will be swallowed whole. And so they're preferentially probing these lower mass black holes that are otherwise very hard to measure. And so most M sigma relations actually don't go low enough to compare well with TDEs. This is one of the few that does, and it utilizes AGN. And you can see it seems to be quite consistent, although there is still a lot of uncertainty in the M sigma relation at these masses. This is exciting. I'm going to give my last couple minutes to talking about the controversy on what produces the actual luminosity in TDEs and how we can use the models that I was discussing to help us understand that. So basically, another way to phrase this question is, where is the luminosity produced in TDEs? Is it produced in the stream collisions and shocks very far away from the black hole, or in the accretion disk very close to the gravitational radius of the black hole? So I compare so another measurement that I get from MOSFET is the efficiency of this, the efficiency of conversion from mass to energy. It's pretty uncertain, however, it's a start. And so here we're comparing it with AGN efficiencies. These are for individual AGN measured from Davis and Lauer's 2011 paper. And we find that for a subset of them, they seem to actually be right where we'd expect super Eddington accretors to be. This band is the approximate efficiency of super Eddington accretion from a bunch of different models and simulations. However, there are these lower, less efficient TDEs. Are those coming? So we want to know if those are consistent with stream collisions. So I also compare them with stream collisions. I'm sorry, I'm going a bit fast here. And if you look at the stream collision rate efficiency at the circularization radius, That is what is plotted in that gray band there. So it's efficiency on the y-axis and the circularization radius over the gravitational radius, which actually is a proxy for the efficiency at the circularization radius. But really all you need to know here is that that gray band is what you'd expect for the efficiency of stream collisions at the circularization radius. So that means everything in red is too efficient to be modeled by, or to be powered by stream collisions outside of the accretion disk radius approximately. But the events in gray are consistent with stream collisions happening right around the accretion disk, which is kind of pushing this model to its limit. Because if the stream collisions are happening right at the edge of the accretion disk, then it's kind of hard to tell that apart from accretion. And so it seems that for a lot of these TDEs, they're more consistent, their efficiencies are more consistent with accretion. And if they were in fact coming from stream collisions further out, we would expect them to have much lower efficiencies. And I'll just leave here, I'll leave here with my summary. Sorry.
Thank you, Brenna Mockler. I apologize again for miscommunicating the amount of time that you had. I think that was an excellent recovery. We don't have time for questions right now, but we don't have any questions right now. But people, you can enter your questions in the Q&A, and Brenna can answer them by text, and or we may have time at the end. So will the next speakers please prepare and start? Our next speaker is DJ Pasham.
Great. Can you see my screen?
I can. Great.
All right, great. So good afternoon, everyone. So I want to share with you a recent exciting result where we've identified 50 million solar mass TDE that also shows multiple accretion states and also transitions between those states in a manner very similar to stellar mass black holes when they go into an outburst, thereby, hinting us that some of these accretion processes are really scale invariant over 7 orders of magnitude in black hole mass. So we know that when stellar mass black holes go into an outburst, an example of which is shown on the right side here, multiple outbursts from an example stellar mass black hole, they have some sort of generic quantitative behavior. That can be shown here in a schematic. They start off in the quiescent state at low fluxes, and as the outburst starts, somewhere near the peak, they transition into the soft state, which means the amount of emission coming out of the systems is really dominated by the newly formed accretion disk. At some point, they transition back into the hard state, where the emission is dominated by the compact corona, and eventually they move back into the quiescence. The same thing can be visualized in terms of a hardness intensity diagram, where on the x-axis I've replaced time with hardness, which is simply the ratio of the flux in the hard X-ray to soft X-ray, or the corona to the disk. And what's important to note here is these transitions in stellar mass black holes happen on the timescales of few hours to few tens of hours. If you were to scale that to supermassive black holes, you expect these transitions to happen on hundreds to even thousands of years of timescale. And that's why we've never seen any single AGN with multiple state transitions. However, TDEs are different, as we just heard. The mass accretion rate changes by several orders of magnitude. So in principle, if we can track them for long enough, we should be able to track all these states. And we think we've identified first a system in TDE where multiple states are seen and multiple state transitions. And we have 3 independent lines of evidence that makes us think that we are seeing these accretion states and transitions. So the first one is shown on the right side here. It's the modified hardness intensity diagram. The source starts in the top left. So I don't know if you can see my cursor. Can you see my cursor? Yeah.
Yes.
Okay. So top left is where the source starts. At the peak, it enters the soft state and then moves into the hard state and eventually goes back into the quiescence. On the left side, I'm showing you 2 light curves. In black is the 2 to 10 keV X-ray luminosity, which is tracking the strength of the corona. And green is the UV, which is tracking the disk. And this behavior, this cycle from going from quiescent, soft, hard to quiescent, that is very similar to what is seen in stellar mass black holes as well, that I showed earlier. Another independent line of evidence is during the soft state. So this is now I'm plotting the fraction of the power law flux in the X-rays as a function of time over 600 days, 500 days. Initially in the soft state, there's essentially no power law, but as it increases in flux, moves into the hard state, the power law fraction strengthens. This is again similar to what is seen in stellar mass black holes. And finally, the variability. Shown here are the power density spectra of the source in the hard state in red and green, which is for two different priors for the model, and soft state is blue. You can see that the thing that is different between these two is fast variability starts appearing in hard state on timescales of as short as a few tenths of minutes. And that is telling us something compact has formed, hinting us towards a corona. So with these three lines of evidence, we argue that we are seeing accretion states. So the takeaway point is this is a new way to look at supermassive black holes, but it does require a dedicated monitoring for several years in UV and optical. And each observatory has had a unique role. And Chandra's role was to really pin down the last observation to say that, yes, it has indeed entered a quiescence. So for that, I would like to thank Belinda and the Chandra DDH team for approving our request. So thanks.
Thank you, DJ. Excellent presentation. We have time, 30 seconds maybe for one question, if we have any questions from the audience. Here we go. What is the significance of the break timescales in your TDE PSD?
So for AGN, people have used that break timescale to estimate the mass of the black hole. And if we use that in our case, we actually get mass that is consistent with M sigma, so which is also sort of encouraging.
Awesome. Great. Thanks a lot, DJ. Our next speaker is Helena Treiber, and I will be giving their slides.
Thank you. Yes, so as you said, my name is Helena Treiber, and I'm a junior at Amherst College. And as a little departure from the theme, I'll tell you about a BE X-ray binary, which I've researched since this summer when I was a Dorrit Hofflet Scholar at Yale. All right, next slide, please. So Eurozita, part of the Russian-German SRG mission, scans the sky every 6 months, but images the LMC repeatedly in that time, thanks to the LMC's proximity to the South Ecliptic Pole, which is an intersection point of the great circles that Eurozita traces. In June, the BE X-ray binary LXP 69.5 was the brightest transient in the LMC. Eurozita's sensitivity and frequent scanning of the Magellanic Clouds will allow for more monitoring and discovery of high-mass X-ray binaries in the coming years. We quickly followed up with NICER, which is on board the International Space Station. NICER has excellent timing resolution and pointing capabilities. Next, please. So this sort of outburst, yeah, can I have the next slide, please? Thank you. So this sort of outburst occurs when the neutron star, which is usually in a wide eccentric orbit around the BE star, reaches periastron and mass is transferred from the BE disk via magnetospheric accretion. At periastron, we usually see both optical and X-ray flares, which originate from the BE disk and the neutron star, respectively. We also see the beamed X-rays as pulses from the magnetic poles as they sweep in and out of view. Next, please. We did spectral and temporal analysis with that NICER data. With the period found with epoch folding, I phase folded the data to create pulse profiles, the properties of which can tell us about changing accretion regimes of the system. At the top, you can see the pulse profile from 2020 in green, looking quite similar to the pulse profile from 2000, the data for which was taken by XMM Newton when the source was in quiescence. This result is surprising because this system was 2 orders of magnitude brighter for our profile, and pulse profile morphology is thought to change with luminosity. On the bottom, we can compare 2 parts of our 2020 data. The profile on the left is about 1/3 brighter than the second on the right, the first being taken near the peak of the outburst and the second a few days later. The red profiles are the softer X-rays and the blue are harder. On the right, we see the higher energy profile is more significantly above the lower energy red, and that secondary peak also became much taller. So with this small difference in luminosity, the pulse profile and hardness changed, whereas the profiles with a much larger difference in luminosity look quite similar. Next, please. And so we also used 10 years of optical OGLE data, although it stopped in March 2020 before the outburst. The optical data shows us the BE disk in particular In most such systems, we see the optical and X-ray flares coinciding, but in this one, despite the face-on disk geometry, which we can find with the V-I relation, the flares do not coincide. The archival SWIFT data in the top long-term X-ray light curve shows the system in quiescence near the brightest overall point in the optical light curve, and then in outburst when the optical is near a minimum. Secondly, the orbital period is still unknown because no single period value is a good fit to the I-band data, perhaps thanks to that additional superorbital long-term trend that you can see. There must be more complex disk precession or truncation effects at play. So I worked on fitting these flares to find their centers and then finding the best model to describe that quasi-periodicity. So rather than a linearly increasing period, for example, I found that the best fit divided this light curve into 3 epochs with different period values. That modeling also supported the optical being near a minimum during the outburst. So if you can just leave my summary slide up, I'd be happy to take questions, and thank you for listening.
Thank you, Helena. Sorry, when I'm sharing the slides, I don't see everything. If you have any questions, please enter them into the Q&A. Okay. So we have a question from Gregory Sivakov. Are there any other potential observations of this source that might fill the times not seen by Ogle?
Yeah, so as far as I know, that's the extent of the optical data for the system. So it goes from March 2010 to March 2020. We did kind of towards the decay of the outburst get SWIFT observations in optical data, but unfortunately the errors were kind of too large to really see the change or if the optical was near a minimum or a maximum, because those changes are kind of small. So hopefully at some point, these observatories will open back up and we'll be able to observe it again in the future.
Great. Thanks so much.
Thank you.
Our next speaker is Dacheng Lin, and he will present now.
Can you see my slides?
Yes, I can.
Okay. Hello, everyone. Thanks to listen to my talk. So here I'm going to present our discovery of two very special tidal disruption events, and we monitor for years. The first one is a decade-long superannuation accretion TDE, and the second one is from an off-centered intermediate mass black hole. And for this decade-long superannuation accretion TDE, we have published the discovery paper in 2017, and we'll publish a follow-up paper soon. And this image shows the host galaxy from Hubble Space Telescope, and you can see that, and the blue circle is the X-ray position uncertainty from Chandra, and you can see that the event is from the nuclear region of a galaxy, as you expected for a typical TDE. But this galaxy is quite special. It is a dwarf star-forming galaxy, not commonly seen in other TDEs. This is the luminosity curve and the X-ray spectrum at different epochs. And you can see that we see a very fast rise and very slow decay in X-ray luminosity. The dashed line here represent how fast other TDEs decay, and you can see that our event lasts much longer than other TDEs. And our event is very numerous in a peak, or not anything limit for a massive black hole. More remarkably, you can there was dramatic spectral change. In the daytime, you see super soft spectral, as you see from other X-ray, typical other X-ray TDEs. But in the peak, the spectra are quite different, and they are still soft, but not as soft as in the daytime soft state. So we call them quasi-soft. And this event is such kind of event is quite special, never seen before. What is it? So here I'd like to show you that many properties of this event seem to support that this is a TDE of a long superantenna accretion phase. I'll go through them one by one and explain why we think so. First, let's see what happens when the accreting black hole is in the super accretion accretion regime. When the mass accretion rate increase to the level that the this luminosity reach the anytime limit, the inner disk would become thick due to high radiation pressure. At this point, new cooling outflow, new cooling mechanism would appear, like outflows and photo trapping effects. Outflow would effectively reduce the mass accretion rate for the inner region, and photo trapping effects occur when the photons will be just carried together into the black hole with the inflow materials instead of being radiated away. So as a result, when we continue to increase the mass accretion rate, the luminosity will just remain more or less at the anytime limit. Then the system will be in the superantenna accretion regime. So, yeah, from the standard theory of the tidal distortion events, we expect the mass accretion rate to go quickly to the superantenna limit and then decay according to T to minus 5/3. So we expect a period of the superantenna accretion when the mass accretion rate is above the anytime limit. And because of what I explained, then we expect that at these periods, we expect an anytime limited luminosity. So in the luminosity curve, you expect a plateau at the beginning of the outburst. And this period can superantenna accretion period can last for about 2 years for full destruction of a solar type star by 1 million solar mass black hole. Then the presence of superantenna accretion phase can explain our events high luminosity around the anytime limit and very slow decay. Then how do we understand the spectral evolution of our event? For this, let's see what happened when a stellar mass black hole in M31 reached the anytime limit. In its 2012 outburst in this stellar mass black hole, the source luminosity reached the anytime limit quickly, and then decreased slowly over months. The plots in the lower panel shows the spectral at different epochs, and you can see that the dramatic spectral change indicate different spectral states. So the spectral was hard at the beginning when it was on rise, and then at the end, when the luminosity decreased, it entered to the so-called thermal state with very soft spectral. But when the luminosity is at the highest point near the anytime limit, the spectral is different. So in such kind of spectral, it seems to be special and it should be characteristic of superantenna accretion state. Now you can compare our event with this set of mass black hole outbursts, and you can from such kind of comparison, you can easily identify. You can see that the spectral evolution in our event is very similar to the M31 source, and you can easily identify the states for our source. So in later time, you see thermal state spectrum with super soft, with very soft spectral, but at a peak, we see our quasi-soft spectrum is similar to the superantenna state spectrum in the M31 source. And at the beginning, our source might have a hard spectrum, but the statistic there is not so good. So from this comparison, you should be convinced that the quality of spectrum here should signature to signal the simple antenna equation in our event. Of course, there are many differences between our event and M31 source. Our event has way much higher luminosity and cooler disk than the M31 source, as expected if our event is due to accretion onto a supermassive black hole. So how do we explain the long duration of this event? If we just based on the standard theory of TDE, we will require of disruption of about 10 solar mass star. Such kind of star is simply too rare, and we don't expect to detect TDE from them, even though this is a dwarf starburst galaxy. But recently, there are many theories, as in the previous talk mentioned, that it looked like it's possible that the circulation, due to the general relativistic effect, the circulation can occur at large radius. So in this case, the time scale of the circulation can be quite long, and you will expect a slow tidal disruption event. And in this case, you will expect of the flat to be fainter, but it lasts much longer than the standard theory. Based on this theory, we just need to have a full disruption of a 3/4 solar mass star with circulation viscosity timescale of 3 years. So hopefully I have shown you that we have discovered a decade-long TDE that so interesting simple antenna equation signature. And this simple antenna equation phase can be characterized by quasi-soft X-ray spectrum. Now I'm going to talk about another TE. It is from an off-centered intermediate mass black hole.
3 minutes remaining.
Okay, and this is a Hubble Space Telescope image too, and of the host galaxy, and the green box show the counterpart of the TDE, and you can see that it is from the it is at the outskirts of a large galaxy, and seem to be associated with a compact star cluster that has stellar mass about 10 mini-solar mass and effective radius of just 27 parsec. And this is the luminosity light curve and the spectral at different epochs again, and it is clear that it is in Outburst and with peak luminosity of 10 to 43 Earths per second. This is very high for an of nuclear source. The X-ray spectra are soft and can be fitted with a standard thin disk. If you try to plot this luminosity versus the inner disk temperature, it is remarkable that the data follow the L to T to force relation as expected for a standard equation disk. This is very important because it can indicate that inner disk radius was truncated at the innermost stable circular orbit. So we can use it to skew the inflow of mass of a black hole and inflow of mass of a black hole to be around 50,000 solar mass. And so it is an intermediate mass black hole. The brightest observation seems to be deviate from the L to T to force 9 a little bit and can be explained if it was in the simple antenna equation phase. The decay of the event seem to follow the standard T to -5 trend as expected for standard TDE. So it is best explained as a TDE, and we can also infer the presence of simple antenna equation phase lasting for about 3 years based on the early time X-ray spectrum and also the optical data. So in conclusion, all property of this source suggests that it is an intermediate mass black hole that went into outburst due to a TDE, making it one of the best intermediate mass black hole candidate. Here, I would like to point out that because intermediate mass black holes TDEs are very rare, so detection of one such event implies that there should be a large population of intermediate mass black holes hidden out there. So this is my talk, and I will thank you very much. I will take questions.
Thank you very much for the excellent talk. We have a couple of questions and we have 2 minutes for those questions. The first question from Miti is, how is the accretion rate of the TDE measured when it is above the Eddington accretion rate?
So, sorry, let me see. The luminosity of the, sorry, should be immunal accretion rate or the luminosity?
Accretion rate is the question.
Sorry, the luminosity accretion rate is hard to measure through there, but we can measure the luminosity. So yeah.
Okay, and then we have another question from Mary Saad. You use the ULX as examples of super Eddington accretion states in black holes, but many ULXs are now known to be neutron stars accreting above the accretion rate due to their intrinsic magnetic fields, which black holes don't have. Can you really use similarity of a TDE to a ULX as evidence for super Eddington accretion when it's not clear ULXs are actually black holes?
That's a good question, but I think people should agree that the black hole, the ULX that I saw from MS31 should be a very strong candidate of accreting supermassive black hole because the spectral in the daytime is just quite, it is very what you expect for thermal state, and for the pulsar, ULX, the spectral are not soft. Okay, so this is very different. So for the one I'm using, that should be quite confident to be from stellar mass black hole.
Great, thanks a lot again for another talk, another good talk. And we have our last speaker lined up now for the session. This speaker is Yvette Cendes, and I'll ask them to now start their slides.
Good.
Great.
All right. Well, thanks everybody, and thanks to Chandra for organizing this conference, workshop. My name is Yvette Cendes at Center for Astrophysics at Harvard Smithsonian, and I'm very excited to tell you guys today about an object that I've been studying a lot and is near and dear to my heart, called Swift J1644 plus 57. The reason this TDE is very famous is, so I was joking to the panelists or the speakers today before we had this, that we all had a different depiction of a TDE or like artist rendition. And the reason this one is special though, is I have a relativistic jet shooting out from my TDE. So Swift J1644 plus 57 is the best studied jetted TDE that we've really had so far since we've been observing TDEs. So what do I mean by this? So Swift J1644 plus 57 was discovered by the Swift satellite on March 28th, 2011. Redshift 3.54, and there were multi-frequency observations that occurred when it was detected by Swift, and it indicated that the star went too close to the supermassive black hole, became tidally disrupted, but it also launched an on-axis relativistic jet that we could see at Earth. It should be noted at the time that two other jetted on-axis TDEs were detected in 2011, just at greater redshifts, and we haven't seen any since. So if anybody can place an order on Amazon so we could see more of these, that would be really cool. But yeah, so this is a very interesting object. It's probably the best studied on-axis, or it is the best studied on-axis TDE. And we still don't really know what caused the jets. Nobody really predicted that jets would happen. And maybe only 1% of TDEs have these relativistic jets. We don't really know the situation there. The other thing that was very interesting, and X-ray observations, including Chandra, were key to discovering for this object, is around day 500 after it was first detected, so about a year and a half after, it was observed that the jet turned off, actually. So what you can see here in this plot is you have an initial variation. This is all Swift data with these data points. We believe this variation in slow decline in X-ray is due to fallback of shredded material that was that basically kept falling onto the black hole and feeding this jet after that initial disruption event. And then what happens though, after 1.5 years, if you look at these last two data points here, so this is the last observation with Swift, and then this is the first Chandra observation for Swift J1644 plus 57. And so there's a very obvious steady steep decline. And there were a lot of questions, what could this potentially be at the time? But what happens though, is if you also have the radio observations, and this is the flux you expect from synchrotron emission that you're going to detect in the radio. If you extrapolate that out, I'm going to explain a bit more in a moment how you do this. You will see that the X-ray is now basically consistent with the sort of flux emission you expect just from synchrotron emission as the shockwave is traveling further out. So that basically was interpreted as the jet turned off. So that was very exciting because of course jets are normally very long lasting from AGNs and things like that. We don't normally see them turn off. So this is a living, breathing example, you know, during the career of one postdoc that you could observe this entire thing. So as I said, multi-frequency data was taken ever since, you know, Swift J1644 plus 57 was discovered. And what we've also been doing at the VLA is we've been observing it in radio. And the reason we're doing this is we want what's called a spectral energy distribution, or SED. And the reason you want to do this is you observe it multiple frequencies, and it's very well modeled how the curve basically, or how the emission evolves over time, basically thanks to gamma ray burst observations of how those jets go out and things like that. So what we're really doing here is you're taking observations at a lot of frequencies, and then we're going to be able to say, based off these various breaks, as the system cools over time, so the peak frequency and the peak velocity will move to lower and lower frequencies, and it will have a continuum all the way down to the X-ray frequencies. And we can really, what we end up using this for is we can then use this to model different things about the system. So you could measure the radius of your shockwave, the energy, the density, and you can even get into the shockwave if you incorporate the radio and the X-ray data together by studying the magnetic field energy density and the electron magnetic field energy density and all sorts of things in the modeling there on what is happening. So it's pretty cool if you combine, as it said, the radio and the X-ray, it's basically all just the same continuum over the electromagnetic spectrum. So what we've done most recently is we've monitored both in radio and in X-ray. It is still observable for sure in the radio. The last update was in 2018 by Tarini Eftenkari, who's on the job market right now, and shout out to her. What she discovered was that it became non-relativistic at about 700 days. So after that jet turned off a few hundred days later, and the emission is dominated, as I said, by that forward shock going outward. We also, so we did these recent observations at day 2493 and day 2795 after the explosion. Just for current reference, we're at day 3481. I looked it up today. It is still consistent with the non-relativistic emission from the forward shock, from the observations we have. You can then, so I had to update some parameters. I decided to focus for my analysis on the non-relativistic period. So after day 700, just to be consistent. And we did a reanalysis of the steepness of that curve that I showed you earlier. In the, it's called the energy index, so P, and that's dependent on the particle acceleration. It was previously measured as P equals 2.5 in the earliest days of the Swift J1644 plus 57 observations. I redid an analysis that showed that P equals 3 is more accurate, so that curve is actually a little bit steeper, which also does affect the X-ray, because then that also affects gamma X photon index and things like that. So I had to update the parameters. You can see here on the right, this is based off of radio data, so the peak flux and various peak frequencies and things like that. You can see that although the data has shifted a little bit, the trends and things are consistent with what we were seeing before. This was all modeled through MCMC to get these. The cooling frequency shifted from 10 to the 15 to 10 to the 13 hertz. But as I said, the nice thing about this is then you can basically model the evolution of the outflow and how this object has been changing over time as the shockwave goes outward. And what we can do is obtain the radius of the shockwave, the energy, co-moving magnetic field strength, total number of radio electrons, and then from that, the density, if you assume certain things about where the emission region is from. The expansion is still consistent with the Newtonian expansion. These are just two of the plots from this analysis. So the radius is still expanding as t to the or t to the 0.1. So it's still a very slow expansion, but it's definitely slowed down quite a bit from its earliest days when it was, of course, still a relativistic system. The energy is steadily also declining. Probably the most interesting thing, though, that's really cool about TDEs is you can take the density. So this density, I basically took this as from, taking the radius, the trend in this radius. So if you're going here, the reason this data point is very large is we had an upper limit on one of our lowest frequencies in that initial SED curve. So then we have big uncertainty. So I just basically took the trend for fitting this data to get the trend in what the density is doing. So it's decreasing still. If you're, this radius is going out, we're around 0.65 parsecs or so from that initial black hole. What is more interesting, however, is we can go and we can look at the density around Swift J1644 plus 57 and compare it to other galaxies that have either been studied because they're closer or have had TDEs that have occurred around them. The scale we use here is not parsecs, but it's the radius of the black hole divided by the Schwarzschild radius. The reason is, of course, not all supermassive black holes are the same size. M87 is very different, say, from the Milky Way. So this is just a way that we can study the density and distance without, having effects from that. What we can see here, so this is, as I said, from the earlier, this is the earlier data shifted for that discrepancy in radius and density that I was showing you earlier on those slides, comparing to the previous observation where P was not 3. But you can see that we are, however, in line, we're decreasing here still in density, but it is not, the least dense. It's still an interstellar or circumstellar environment consistent with other galaxies that we see around us. These two are TDEs that were kind of the other two that have been probed out the furthest. However, they are non-relativistic outflows is the current interpretation of what's going on. It is very interesting to wonder, if these densities are going to also be consistent as we're going out in these galaxies or things like that. I also just find it pretty amazing if you think about it. So Swift J1644 plus 57 is, I guess, if you convert the Z, about 3.5 billion light years from us. And we have this amazing sampling of what the density is around this galactic center of this galaxy so far away from us. So that's pretty incredible if you think about it. But yes, that was the radio. This is, of course, an X-ray workshop. So I was also going to tell you guys about the X-ray observations that we had with Chandra. So we had two observations. Okay. 2 observations, 50 kiloseconds each. Unfortunately, however, no emission was detected. So these 2 data points are basically new to this work. However, I did have to recalculate all the fluxes here and updated them based off the earlier findings from earlier observations, just to take into account the correct, the updated photon index. The interesting thing, what you can do is, as I said, if you have that radio data, extrapolate that curve all the way out based off of where we find that cooling frequency. You can play around with what epsilon B is going to be the magnetic field energy density. And what we found was the best match was if epsilon B, it was 0.01. Normally you say epsilon B and epsilon E are 0.1. So this is called a deviation from equipartition, which is very interesting physics-wise, that we can actually even get into the physics of what is going on in this shock wave. The good news is, even though we can't see it currently anymore in X-ray, we can still see it in radio, and we're probably going to for a very long time. These are the new observations. As you can see, it's fading faster at higher frequencies, but say at 1.5 gigahertz, this is going to be an object that will, give many future PhDs and postdocs something to study, I think, if you want to keep going back and monitoring how this shockwave is going out and interacting with its environment. So that's going to be pretty exciting to see in coming years. And as I said, hopefully we'll find some other jetted TDEs that we can also study how those evolve. So just some conclusions. So there's a paper that it's going to be submitted either this week or next week. This was my draft conclusion until I realized the referee probably would not like the draft conclusion that, the subject is fading in the sky, but will never fade in our hearts, because it really is just such a seminal TDE that's been very well studied because of its jet and its environment. It was so bright and so many frequencies. It is incredibly still radio visible almost a decade later, but it is no longer visible in X-ray. As this forward shock continues outward, the emission is still there, but just decreasing over time. And it's still going to be a benchmark for relativistic TDE for many years to come in the future. So thanks very much, and I'll take any questions.
Great, thank you. That's a lovely conclusion. Okay, we have a question from John Matthew Miller. Estimates of TDE detection rates are often based on catching peak fluxes. If other jetted TDEs follow the trend seen in Swift J1644, will SCA detect a number of jetted TDEs only based on late time decays?
So this is actually interesting. I didn't have time to get into in the talk, but in the paper, there's actually, we had a VLAS, so Very Large Array Sky Survey. We had 2 detections already of this object in VLAS, and you can actually calculate how many you should see, you know, say the Very Large Array Sky Survey. Of course, SKA is going to have much greater sensitivity. Even something like VLA Sky Survey, we concluded you should have, based off the light curve, how this thing evolves, you know, a handful in the Sky Survey. So something like SKA is going to be like a factor of 10 more. So there will be, you know, at least a few dozen or something, I'd say.
Great. Any more questions from the guest attendees? I had a question about your non-detections with Chandra.
Mm-hmm.
Is it something where a deeper exposure won't get down to the sensitivity limit you need?
It might, I guess, but yeah, you know, then you have to apply for or longer exposures.
Right, right. And what about with other instruments like XMM?
We haven't really looked into that, to be honest.
Okay. Great. I have a question. You have time. So you were showing us the plot that where you're normalizing by the Schwarzschild radius.
Mm-hmm.
And I was trying to get in my head what that means, and in terms, you explained it a little bit, but could you elaborate a little bit more? Is it kind of giving you like the influence of the system in the core?
It's basically you're trying to account for the fact that, you know, you could have a supermassive black hole that is 1 million solar masses versus 10 million solar masses. So if you're dividing by the Schwarzschild radius, so the overall size of it, then hopefully, you know, then it's going to be at least some sort of standard where you're taking out the size of the black hole into a distance calculation. Because as I said, like 0.65 parsecs from this black hole is not the same as 0.65 parsecs from another black hole, right?
Mm-hmm.
So does that make sense?
Yeah. Okay. And one question from Mike Novak. If the source is relatively isolated, XMM can give you, well, this is more of a comment than a question, XMM can give you more bang for the buck on detection limits. This is true. It has a bit more sensitivity. And I think the deadline's coming up this week.
Oh, well, this week. Okay. I'll see what I can do. But thanks for letting me know.
Right.
Yeah. I mean, I guess the good thing is it's probably not going to change much in brightness between this year and next year. So we'll keep that in mind.
Great. Thank you so much. Thank all the speakers. We do have a little bit of time. I'd say 2 minutes. If anyone has one last question for anyone, we can try to field it. If not, I want to thank the speakers again for an excellent session. I'm sorry about my miscommunication on the time for Brenna Mockler's talk. I think that the recovery was excellent. Thank you all. Join us tomorrow morning at 9 a.m. Eastern time when we will have our panel discussion on synergies with 4 panelists who will talk about different synergies with different instruments. Thank you. Bye.